Fundamental Theorem of Calculus. Summary of what we did on the front side. We're looking at the integral of this function t squared with respect to t, lower bound of a, upper bound of x, and we determined that the integral was 1/3 x cubed plus some constant, and that constant we are calling c. And again, tucked into this constant is the 1/3 a x to the third. So three things to note about this. All right, so thing number one is that when we're looking for this integral, what we have, we could say that it is a function of x, not t. All right. So we have tucked into the integral a function of t. We're integrating with respect to t. Excuse me. But the upper bound is what our variable is. And when we're all done, we end up with this function here, 1/3 x cubed plus some constant. And this is a function of x. Observation number two, really what we've got here is an antiderivative, right? So it's an antiderivative of x squared. Where the a is like c. Right? Both of them are constants. Right? And then the last thing to notice here is that if you take the derivative of this function, right? So up here, right, ax is equal to all of this. We simplify this and we get this here, which is to say that this here is ax. And then if we take the derivative of ax, right, so a prime of x, it's going to be equal to, well, it's the derivative of this, which is x squared. Which is to say that, and here's the important observation, that if you have this integral that goes from a to x of the function t squared with respect to t, and you take this and you take the derivative of this with respect to x, right, which is what this is, right? So this part here is our ax. We take the derivative of it, and we end up getting x squared. All right. Okay, so some examples. Excuse me. The integral from 0 to x of cosine t with respect to t is going to be sine x minus 0. Upper bound minus lower bound, antiderivative of with the upper bound as the input, antiderivative with the lower bound as the input. The derivative of all of this is going to be the cosine of x. Right? Again, this piece here, the integral, is really a function of x. When we take the derivative with respect to x, we get cosine x. C. Lower bound here, pi over 2. So this is going to be sine of x minus the sine of pi over 2, and the sine of pi over 2 is 1. Right? So just a note, just to make sure you're following that. This here comes from this fact that the sine of pi over 2 is equal to 1, right? Which comes from here, the lower bound. D, excuse me, if we are taking the derivative of the integral and the upper bound is our variable, lower bound is pi over 2, the derivative is, again, just like the one right up above it in B, the derivative is cosine x. All right, and then the last one, the lower bound here, 19 pi over 37. Upper bound is our variable. We're integrating, then turning around and taking the derivative, and again, we're getting cosine x. So notice that the lower bound makes no difference in these. Okay, so here we go. Formally, we now will write out the second fundamental theorem of calculus. Right? So the second fundamental theorem of calculus looks like this. The derivative with respect to x of an integral which goes from some constant a to a variable x a function of some other variable, and in this case we're using the variable t, right? So this is with respect to t. This is going to be equal to f of x, x being the upper bound. Right? So there it is, the second fundamental theorem of calculus. Okay, so what kind of questions will you see on an AP exam that use the second fundamental theorem of calculus? So we have 5 of them down below. So the first one here for 5A, I'm going to go through it the long way, and then we'll the next two we'll just kind of use the pattern that we're noticing here. So if we take the integral of secant squared t dt, well, that's going to be the tangent of t from lower bound of 2, upper bound of x, and then we'll end up taking the derivative of all of that, which then is going to be the derivative of, and we're going to take the upper bound, tangent of x, minus the lower bound, tangent of 2, take the derivative of that. This is going to be a constant, and the derivative of this, of tangent x, is going to be secant squared x. Right? So notice what's happening here. The reason that the t is being replaced with an x is because the x is the upper bound. And when we integrate, right, so we're taking the antiderivative, which gives us the tangent of t. When we integrate upper bound minus lower bound, the x ends up being plugged in here at tangent x. And then when we take the derivative of the tangent x, we end up getting back to secant squared, but now it's of x. Right? So that's why the t is being replaced with the x. Right? So once we see that pattern, then it's pretty easy to see for b here that the derivative of the integral of will end up simply being x cubed times x to the 4th plus 9 all to the 5th, and the integral of the derivative of the integral of 5t with respect to t, lower bound of 2, upper bound of x, is going to end up being 5x. Alright, so for the last example before we do this, I want to just make a little sketch of this function here, and actually let's just tidy this up for Mr. Friedland. This should be with respect to t, this integral with respect to t. So I'm going to use this space up here to just draw what we've, this function that we've got, right? So we've got a function that looks like this. We got a parabola. It's got the points that are of interest to us. This is 4, this is 1, this is 4, and then we're looking over here at -3. -3 is our lower bound. Right? And we'll bring this up a little bit higher. Okay. Excuse the sloppiness of this. So what we're looking at here, the function f of x, is a function that's looking at the area, starting area between the curve and the x-axis, starting at -3. Right? So we're looking here. So if we were, say, at -1, this would be the total area. If we were at 0, right, this would be the total area. If x was 1, the total area would be here. And this is the area between the curve and the x-axis. Right? Now, what happens here is that when we get beyond 1, then we have down here negative. The area is below the x-axis, so it's going to end up subtracting from the area that's above the x-axis. Right? So if we were to look at how much total area we had, say, at 2, then it would be that green area up here minus this. And then we're going to, as x increases, we're pushing the outer edge here of the total area off to the right. Right? And you can see from this graph that the f of x is decreasing. Right? So this area, that's the total accumulated area, is going to get smaller between 1 and 4. Right? Now, if you didn't have this picture, if you didn't take t squared minus 5t plus 4 and graph it and do the analysis that I just did, you can still do this by taking, just going back, and we'll do it in this color. Taking the derivative of f And again, f is a function in terms of x. So when we take the derivative of this, well, the derivative of this is equal to x squared minus 5x plus 4. You can factor this into x minus 1, x plus 4, and then you do the number line analysis here. 1 here, 4 here. To the left of 1, we have the derivative is positive. And this is, again, this is the derivative of our f function, and the f function is the total accumulated area as we start from -3 and head to the right. So it's positive here, negative here, and positive here. So then from the number line analysis, we can see that f of x is decreasing its derivative. Right? So the derivative of f of x is negative between 1 and 4. Right? So between 1 and 4. Right? And if we want to figure out when it's concave down, we look at the second derivative. Right? So the second derivative here is going to be 2x minus 5. We have a dire point at 2.5. We do a number line analysis for the second derivative at 2.5 here. To the left of 2.5, the second derivative is going to be negative. To the right, the second derivative is going to be positive, and the function f of x, and again, this here, this red line, is not the function f of x. This is the derivative of f of x. The function f of x is some function that relates where I am along the x-axis after having started at -3 to the total accumulated area. But this the function f of x is going to be concave down when x is less than 2.5. And we are done with the backside of the second fundamental theorem of calculus notes.